Hello everyone, my name is Jun Yang. I'm from Peking University, Beijing, China. Today I will talk one-dimensional and three-dimensional model integrations on the simulations of water vapor and clouds on habitable planets. This work was done with Jeremy, Colin, Nico, Tim, Yuwei, Daniel, Feng, Francis, and Dorian. Most part of this work was finished when I was a postdoctor at the University of Chicago. Dorian was my advisor. My talk has three parts. The first one is about one-dimensional Radiative-transfer model comparisons, and the second one is about 3D atmosphere general circulation models. Finally, I will briefly show some other facts. For the one-dimensional Radiative-transfer models, we use 7 models. 2 of them are line-by-line models, and 5 of them are from 3D atmosphere general circulation models. The 2 line-by-line models are LBL, RTM, and SMART. When do the 1D Radiative-transfer calculations, the surface and air temperature are fixed, and the water-vapor mix ratio are also fixed. Clouds are not included in the simulations. These figures show the outgoing longwave radiation as a function of surface temperature. As you can see that in low temperature, the difference between the models is very small, but the difference became larger and larger as a function of surface temperature. At high temperature, the difference can be as large as 25 watts per meter square. This is due to that the CO2 and water vapor continual observation in high temperature is quite different between different models. Besides of the difference in long wave, there are also large difference in the short wave. These figures show the stellar spectra as a function of wavelengths. As you can see that in CAM3 and AM2, the resolution of the stellar spectra is very low. This can influence the shortwave observation by water vapor, so the resolution of the stellar spectra is very important when consider the radiative-transfer of water vapor. These figures show the TOA upward shortwave radiation as a function of surface temperature and the surface downward shortwave radiation as a function of surface temperature. In both panels, we can find that the difference in shortwave radiation is large. It can be as large as 100 watts per meter square. This difference is mainly due to the difference in water vapor observation. In 3D ExoCAM comparisons, we use 5 models. These models have different resolutions, different dynamic cores, as well as different cloud schemes. In these simulations, the boundary conditions are the same. We use M star, and the rotation period is 60 Earth days. The atmosphere is Earth-like with 1 bar nitrogen and some CO2. The surface is set to Exoplanet with an ocean depth of 50 meters everywhere. Also, the surface albedo is the same between the models. First, we do 2 dry dynamical experiments. In this simulation, there is no water vapor or clouds. This figure shows the meridional mean surface temperature as a function of longitude. This is for tidal rock planets. We can see that the difference between the two models, CAM3 and MTG, is very small in dry dynamical. In global mean, the surface temperature difference is less than 3 Kelvin. So we can see that the difference in dry dynamical is unlikely to have a strong effect on the surface temperature. But when water vapor and clouds are included in the simulations, the difference between the models can be very large. In global mean, the surface temperature can be as large as 14 Kelvin between the models. The left panel of this figure shows the results of no cloud simulations. We see low clouds, which means that in these simulations, the cloud radiative factor are turned off, but there is still precipitation in the model. We can see that on the night side, the temperature difference can be as large as 14 Kelvin, and on the day side, the temperature difference can be as large as 20 to 13 Kelvin. When clouds are included in the simulation, the right panel, the difference between the models also very large, especially between the CAM models and the MDG models. There are several reasons for the difference between the models. The first reason is the difference in cloud schemes. The upper panel shows the cloud coverage between different models. The lower panels show the cloud water path between different models. In all these simulations, there are strong convection clouds over the substellar region. So this type of planets has a high planet albedo. But there are very large differences between the models in both cloud coverage and cloud water. Even in the same model, LMDG, when we use two different cloud overlap schemes, the maximum cloud overlap or the random cloud overlap, there are also very large differences between these models, especially for the cloud water path. The second reason is about the relative humidity. This figure shows the relative humidity as a function of pressure and longitude for different models. Both the case of low clouds and with clouds are shown. We can find that there are very large differences in the relative humidity. In AGCM, the relative humidity can be related to large-scale circulation, convection, shortwave observation by water vapor, or other facts. As we have already shown that between the models, the shortwave observation by water vapor has a large difference. So we do some sensitivity test by increasing the shortwave observation coefficients in the model. When we include the shortwave observation coefficients, the surface temperature increases. Meanwhile, the relative humidity also increases. We have also do some simulation with fixed SST, but increasing the shortwave observation coefficients, we also found that the relative humidity increases. We also have done simulations with different model resolutions, use the ExoCAM. When we increase the horizontal resolution or the vertical resolution of the model, we find that the change of global mean surface temperature is less than 5 Kelvin. So we can see that Horizontal or vertical resolution is not the key part of the difference between the models. A key question is, how large do they affect the uncertainties in estimating the inner edge of the habit zone? Based on the following 4 papers, I summarize that for water vapor, the effect could be as large as 100 watts per meter square in global mean for M stars. And for clouds, its effect could be as large as 215 watts per meter square in global mean, also for M stars. For G stars, their effects would be smaller. There are several other effects can influence the simulated climate. For example, the oceanic heat transport. When ocean dynamics are included in the simulations, the surface of the night side became much warmer than the case in the atmosphere-only simulations. Meanwhile, the day side became a little cooler. These results show that ocean heat transport can strongly affect the climate on the night side. This is the simulation for planets in the median region of the habitable zone. For planets close to the inner edge of the habitable zone, the effect of ocean dynamics is much smaller. You can read the paper below. Another effect is about sea ice drift. Because of the winds, the sea ice can flow from the night side to the day side, so it can influence the climate. This figure shows the simulation of 3 planets under 3 types of simulations: atmosphere only, atmosphere plus ocean, atmosphere plus ocean plus sea ice drift. As you can see that the blue color is for open ocean, the white color is for ice. When ice drift is included in the simulation, the sea ice concentration increases a lot. In some simulations, the sea ice drift even pushed the system from an eyeball-like state to a globally ice-covered snowball state. So, sea ice drift is important, especially for planets close to the outer edge of the habitable zone. This is the summary of my talk. Through one-dimensional and three-dimensional model comparisons, we found that the largest difference is from clouds. Also, there are large differences in water vapor radiative-transfer for both long wave and short wave. In the short wave, the difference is even greater than that in the long wave. For the short wave radiative-transfer, stellar spectral resolution is important. So, future work should increase the stellar spectral resolution in order to more exactly calculate the radiative-transfer of water vapor. Finally, we show that the effect of dry dynamic core and the effect of different spatial resolution of the models on the surface temperature are small. For future work, I suggest that cloud resolving simulations should be used for exoplanets. Also, besides of the atmosphere general circulation models, more attention should be paid to ocean heat transport and the sea ice drift, as well as the ice and snow albedos. Thank you very much.